Welcome to another MVC screencast. Today we want to talk about work integrals. But before we start, we should probably start with just talking about what work is. So you'll remember from probably first semester of physics that work is force times distance, right? Force exerted over some distance, the measure of change in energy in your system, right? You can go right now to your wall and exert as much force as you can against it, and it probably won't move. And so while you may get tired, you will not have done any work. Now, this very simple formula is applicable to very simple situations, like, say you're going to move a box across the floor, and so you push on it parallel to the floor for a given distance. So that's fine. Find the force times distance, you're done. There's your work computation. But the world isn't usually that simple. Right? For one thing, not all your force usually goes in the right direction. So let's just change this up and look at pushing a box up a slope here. So maybe you push on it horizontally, but the slope goes up. So what really happens here? Well, a simple force diagram will tell us. We've got the force, and we'll imagine it being pushed against the center of the box on the ramp here. And then there are two directions that we want to identify for where it's going to go. There's the direction normal to the surface and the direction tangent to the surface. We'll call these N and T, and consider them as unit vectors in those respective directions. Now, the normal direction of the force, right, we'll point down, that's countered by the ramp itself, right, pushes back. And so those cancel out and don't contribute at all to the work. The only part that contributes to the work is the part that goes in the tangent direction, in the direction of the path of the box up here. Right, so know how much force goes there. That's just a scalar projection. Right, we want to project our force in the direction of t. And since t is a unit vector, this is quite nice. We find out that's just f dot t. Right, so that dot product, again, smaller than the magnitude of f is what the force that we want to measure is. And so if you just multiply that by distance, keep it constant, we'll get work. But then you realize that, oh, well, it's hard to keep forces constant, especially when you get tired pushing something up a hill. So after you push it a little bit, you may be exerting less force, or it certainly can change as you go. So what you end up doing is to approximate how much work is done. We're going to multiply our distance by a little bit of distance, delta S. And of course, then force might change, so we reevaluate, and we do it again, and compute, and again, and again. And of course, we're just going to add all those up. And we've seen this expression several times. That looks like a Riemann sum. It is. To get a better approximation, we translate from Greek to German. That is, we're going to do a line integral. Right? So the path that the box moves will be represented by c. And then we're integrating this scalar quantity, the projection of my force in the direction of the curve. And then I integrate with respect to arc length, that delta S becomes ds. But we've seen this expression before. In fact, we can simplify this by just considering the line integral through the vector field given by the force. It's all captured in the expression for the line integral through a vector field. Again, c is the path of the box, the force is the force you're exerting, and if we just do dot dr, it captures all the amount of the force that pushes in the direction that the box goes. So once we identify the force and the path, that's all we need to compute work. So here's the exercise we're going to look at. It looks simple enough. We've got a wagon 5 meters away, and we're pulling it from a rope that's a meter above the connection point. And we're just going to yank on that rope with a constant force of 7 newtons until it gets all the way to us. Right? So it starts back here, and we just yank it, constant 7 newtons, yanking at it, it gets here. Now that may sound like a simple non-calculus problem until you consider this idea that the force has to be measured in the direction of travel, in the direction of the path. So the path is horizontal here, and the force is 7 newtons, right? But pointing up along the string, the tension in the string points this way. That's changing, right? That doesn't change. However, the projection in the direction of travel, right, remember f dot t, does change. Right? It's less efficient over here than it was at the beginning, and in fact, the closer it gets, the less my pulling, less force my pulling exerts in the direction of travel where we want to go. So we definitely need an integral to do this. That force in this direction is changing at different places on the interval. So to model this problem, we're going to need some axes. You've got a lot of choices here, but I'm going to put mine oriented this way because then the place that the wagon's being pulled from is stable at the point 0, 1, simply. And then the part that's moving is the front of the wagon at a general point x, y, but I know ahead of time that this is just going to travel along the x-axis, so y will be 0 in this example. So I need to find the force as a function of that position, right? F of x and y for different positions of my wagon. Now it's said in the problem that I'm always pulling with a force of 7 newtons, but what's changing is the direction, right? It depends on where the wagon is. So the direction of the force, really the tension in the rope, will point from that position x, y to the point 0, 1. Right? So we need a unit vector u here that always points from x, y to 0, 1. Well, we know how to do that. Good old subtraction will get us in the direction that we want to go, and then we normalize to make sure that u is the right length there. So there's a vector that points with magnitude 7 in the direction of 0, 1 from any point x, y. We can clean this up a little bit, pull out the scalar terms. We're left with 7 over a square root of x squared plus 1 minus y squared minus x comma 1 minus y. Now I'm going to tell Mathematica that that's the f I want by using the function. I define f. Its inputs are x and y, and its output is as described here. Now one really nice feature of this modeling of our force field is that it works for any position of the wagon. We know ours is just going to go back and forth on horizontally, but if I change my terrain, say, and I've got a wagon that's going to be pulled over a couple of bumps here, that same force term is going to work. Wherever the wagon is, the force is always going to be 7 newtons in that direction. So to do different work problems on different terrains here, I can use the same F value. I just need to change the path of the wagon, which is pretty neat. The hard part is done. All I need to do is parameterize the path of my wagon here, which I'll call C. Couldn't be easier. It just travels in a straight line. And here's the thing. We just need to parameterize the path. We do not need to accurately reflect how the wagon will move in time to compute work. Right? That's a harder problem to do. Our task is easier. We just need to parameterize the path. So that t really doesn't represent time here. It's just a parameter that will trace out this path starting from 5, 0 back to the origin at 0, 0. That's easily accomplished with a linear function, just 5 minus t, 0, on the interval 0 to 5. And we're also going to need the tangent vector here, which of course is just minus 1, 0, pointing back toward the origin. All that's left to do is to compute. So let's again recruit Mathematica for that. Let's see what let's compose our vector field with the path. So that's f at 5 minus t comma 0. And we can see there's the force changing in according to our parameter, and we can dot it with r prime of t to see what our integrand is going to be here. And there it is. That's the amount of the force pointing in the direction of the path. And lastly, we just need to integrate this function from 0 to 5. Pull it in there. dt 5, we'll leave the dots so that we get a real number. And there's our answer, about 28.7 Newton meters.